Okay, good morning, everyone. Sorry I couldn't be there this morning. I'll be back this afternoon. Something has come up that I need to take care of. So I'm making a video of the lesson that we're covering today. What this means is that any questions that you have from yesterday's lesson are going to have to wait until tomorrow. But I would ask you to please do me a favor and in preparation for tomorrow's class, get organized and get a list of any questions that you have from the assigned problems so that when we get started tomorrow we can answer them as a group. We're looking at section 11.3 here. This is the final topic in this unit, which means the final topic in this course. It's on what's called the Binomial Theorem, and I'm breaking it down into 2 days. So we're going to be finishing the unit tomorrow, which is Thursday. On Friday and Monday, we're going to be reviewing, and your unit exam is next Tuesday. We're going to be using Pascal's triangle along with patterns to expand out binomials that look like x plus y raised to the n. So for example, a binomial that looks like x plus y raised to the n would be x plus y raised to the 2. And you certainly don't need 30-level high school math to figure out what that is. You understand that that's x plus y times x plus y. What that means is that you FOIL it out, and I'm not even going to discuss how we're getting that. That should be like taking candy from a weak and tired baby. You get x squared plus 2xy plus y squared. If, on the other hand, I said to you, go ahead and expand out x plus y to the 6, I decided for whatever reason that I wanted to keep everybody in the room busy for the next 25 minutes or so. What that means is you're asking yourself, what is that equal to? And you would have to do repeated multiplication. You would take the first x plus y times the second x plus y to get x squared plus 2xy plus y squared. Then you would have to multiply that by the third x plus y and simplify it, at which point your head would be spinning because it's going to be getting very complicated, and you would simplify that. Then you would multiply it by the fourth x plus y, on and on down the line until you were done. And that would be torturous. It doesn't have to be x plus y. It can be any binomial. It could be 2a minus 4b, quantity raised to the 4. And the binomial theorem is what we would use to figure out what that's equal to. It doesn't have to be a linear binomial. The binomial itself could be quadratic. In this case, we have 3y minus 7y squared raised to the 3. Well, the question is then, what is that equal to? And this is what the binomial theorem is a way for us to expand these out without the heartache of having to expand it out step by step. Think of it as a set of shortcuts that will take us to the expansion. In order to introduce ourselves to these patterns, we're going to be starting by looking at something called Pascal's triangle, which is simply an arrangement of numbers that can be used in many mathematical operations. And it's a triangular arrangement of numbers. I happen to be giving you the first 5 rows. I want you to make a note, and it can actually be a written note if you feel you need to, because it's a very important note, that the number of entries in each row of Pascal's triangle matches the row number. Like, let that sink in. If I said, how many numbers are in the first row, the answer is 1. The number 1 is there. If I said, how many numbers are in the second row, the answer is 2. There's a 1 and another 1. The third row has 1, 2, 1, which is 3 numbers. The fourth row is 1, 3, 3, 1. That's 4 numbers. The fifth row has 5 numbers. And the question is, complete the next 4 rows of Pascal's triangle and explain how each entry is arrived at. Well, if I were in class, I would give you a minute or so to ponder that, but I don't know how to proceed without looking at the reactions on your faces, so I'm just going to tell you what the pattern is. The pattern is that you add the numbers immediately above an entry to figure out what that entry is. And I'm going to let this run through a couple of times without talking. So if you want to know, and by the way, it's pretty obvious that all of the rows start with 1 and end with 1. I suppose I should have mentioned that right out of the gate. All of these rows start with 1 and end with 1. But if I wanted to know what number I'm going to put in here, I look immediately above it and I see a 1 and a 4, and that tells me that I'm going to put the number 5 there, because 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. I'm going to complete the final 3 rows in our diagram here without talking. You can go ahead and complete them on your handout, and then you can look up here and confirm that you're getting the same result. Now I'm adding these without a calculator, and even though the numbers are small, you know how easy it is to make a mistake in math. So I'm just going to step back and take a look at the numbers I've written. And they look okay. So that's what Pascal's triangle is. Now what does this have to do with expanding binomials? Well, if we take a look at the diagram for number 2. Now, your diagram in number 2 is already completed. I want you to focus on the screen though. In number 2, at the top of the screen, it says x plus y to the 0 is 1. Well, we know that's true because any base to the 0 other than 0 to the 0, which is not defined, but that's not really relevant. A binomial raised to the 0 is going to be 1 by definition. If I take a look at x plus y, the binomial raised to the 1, well, that just means it's x plus y. It's 1x plus 1y. X plus y squared, we've already established that that's x squared plus 2xy plus y squared. X plus y cubed, I do want to show this to you. If I said, what is x plus y cubed? Here's what you would need to do. And you don't write this down. There's no need to. Just focus on the screen. You would say to yourself that that's x plus y multiplied by itself 3 times. You would multiply the first pair of binomials, the x plus y and the x plus y together, to get x squared plus 2xy plus y squared by FOILing it out. And then you would proceed to multiply that trinomial by the binomial x plus y. And what you've been taught in previous classes is that multiplication is a distributive operation in math. What it means is that every term in the first polynomial, which is a trinomial, will be multiplied by every term in the second polynomial, which is a binomial. I'm going to have 6 products here. I need to take x squared times x, which will give me x cubed. I need to take x squared times y, which gives me x squared y. Now I'm on to 2xy times x, which gives me 2x squared y. 2xy times y, which is 2xy squared. Y squared times x, which is xy squared. And finally, y squared times y, which is y cubed. And I add all of those things together. I have an x squared y plus another 2x squared y's, which give me 3x squared y's. I have 2xy squareds and 1xy squared. That gives me 3xy squared. So the bottom line is that x plus y quantity cubed is x cubed plus 3x squared y plus 3xy squared plus y cubed. And that's why at the beginning of question 2, I have this diagram. I want to point out some things to you, and these are very important in this lesson. You cannot proceed in this lesson without understanding these basic ideas. That if the exponent on the binomial is 0, then you get 1 term in the expansion. If the exponent on the binomial is 1, you get 2 terms. When I have x plus y to the 1, I get x, which is a term, plus y, which is a term. When I have an exponent of 2, I get 3 terms. When I have an exponent of 3, I get 4 terms. So I want to summarize this verbally. You don't need to write this down because this is in your notes on the next page, which we'll get to. The number of terms in the expansion of x plus y to the n will be 1 more than n. Let that sink in. If I said how many terms are in the expansion of x plus y to the 12, there would be 13 terms. The other thing I want to point out to you, and this is just, well, it's more important, I think, than the point I just made, is that these numbers, the coefficients of everything, are the numbers from Pascal's triangle. And there's one more thing I want to point out to you, and I'm going to be using x plus y cubed, quantity cubed, to illustrate this, is that the exponent on x in the first term is 3, and the exponent on x in the second term is 2, and then the exponent on x in the third term is 1, and the exponent on x in the final term is 0. In fact, I could write this out, everybody, as 1x cubed y to the 0 plus 3x squared y to the 1 plus 3x to the 1 y to the 2 plus 1x to the 0 y cubed. And I'm pointing out to you that in the first term, x has the exponent that is on the binomial, and the exponent on y in the first term is 0. And then what happens is every time I go left to right one term, the exponent on x decreases by 1, and the exponent on y increases by 1. So it goes from an x to the 3 to an x to the 2 to an x to the 1 to an x to the 0 at the same time as it's going from y to the 0, y to the 1, y to the 2, y to the 3. There's all kinds of important ideas here. Let's use this to find the expansion of x plus y to the 4, and then we're going to verify the answer. Well, x plus y to the 4 will have 5 terms. And I feel as though I want to back up and really make this point. The green numbers are the numbers from Pascal's triangle. I don't think I really sold this point. The green numbers are the numbers from the row in Pascal's triangle. So the coefficients in x plus y quantity cubed are 1, 3, 3, 1, which are the numbers from the 4th row of Pascal's triangle. If x plus y to the 3 has to have 4 terms, then we need to look in Pascal's triangle at the row that has 4 numbers. Well, this is row 4 of Pascal's triangle. So if we want to expand x plus y to the 4, and we know it has 5 terms, we need to look at row 5 of Pascal's triangle. Well, you can flip back and look at row 5 on your diagram. I'm just going to look at row 4 and generate row 5 from it, and you will get 1, 4, 6, 4, 1. So row 5 is 1, 4, 6, 4, 1. Those are the entries in row 5 of Pascal's triangle. So x plus y to the 4 will contain 1. The coefficient is the first number in that row. It will contain x raised to the 4, and it will contain y to the 0. My next term is going to contain a coefficient of 4. It will contain x cubed, y to the 1. So x is losing an exponent each time, y is gaining an exponent each time. Then 6, and it will be x squared, y squared. And then 4, it will be x to the 1, y cubed. and then finally back down to 1, it will be x to the 0, y to the 4. There's certainly a lot we don't need to write here. To clean it up, we can do the following. I don't need to write the 1, and I don't need to write the y to the 0. In the second term, I have y to the 1. Well, that's just y. Then I have 6x squared y squared. Then I have 4x y cubed. And then I have y to the 4. You can do a double check. Do we get 5 terms? Yes. Does the first term contain x to the 4? Yes. Does the exponent on x go down by 1 each time? Absolutely. Does the exponent on y go up 1 each time? Yes. And are the numbers we put in front the numbers from the 5th row of Pascal's triangle? Yes. So if you turn the page, please. Oh, I'm sorry. I said we were going to verify this. I'm going to verify it not by expanding it out, but by entering in x plus y to the 4 into Wolfram alpha. Apparently the internet is very slow right now. There we go. It gives us a number of pieces of information, but the most important piece of information is an expanded form. It tells us that it's x to the 4 plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4, convincing you that it's true. I mean, I would never teach you something that wasn't true, but the bottom line is we were asked to show that it is true. So, here are the rules that we use to expand binomials by looking at Pascal's triangle. I say it that way because there's another way to do it that we're going to start learning about a little bit later. There will always be n plus 1 terms in the expansion of x plus y to the n. So if I have x plus y to the 4, there's going to be 5 terms. Since the coefficients of the terms are the numbers in a row in Pascal's triangle, and we need one more term than n, you have to go to the n plus 1th row of Pascal's triangle. If you need 7 coefficients, you have to go to the 7th row. By the way, if you need 7 coefficients, you're talking about x plus y to the 6. The first term will always contain n for an exponent on x. So if it's x plus y to the 6, the first term will contain x to the 6, and it will contain y to the 0. Each subsequent term loses 1 for the exponent on x and gains 1 for the exponent on y until you run out of x's and you have all of the exponents carried by y. Let's use that now to expand x plus y to the 5. Well, that's going to be, since n is 5, that means there are 6 terms. We need to look at the 6th row of Pascal's triangle. Now you can go back in your note package and look at the 6th row. I'm simply going to take the 5th row and build the 6th row from it. The 5th row was, I believe, 1, 4, 6, 4, 1, which will give me 1, 5, 10, 10, 5, 1. I feel as though since I can't ask you to double check, I'd better go back and just make sure that that's right. 1, 4, 6, 4, 1 would give me 1, 5, 10, 10, 5, 1. That's correct. So, x plus y to the 5. We will have 1 x to the 5, y to the 0, plus 5 x to the 4, y to the 1, plus 10 x cubed y squared. What's happening each time is x is losing 1 for an exponent, y is gaining 1 for an exponent, and I'm loading in from Pascal's triangle these 6 numbers for the coefficients. I have another 10. This time it will be x squared y cubed. Then I'm back down to a 5, which will be x y to the 4. Finally, I'm at 1, and it will be y to the 5. And that's our answer. I'm just double checking everything. One of the things I'm doing is making sure that when I add up the exponents for any term, I get 5. It looks okay. B is 3r minus 2t to the 5. So what's happening here, everybody, is our x is not x, it's 3r. Our y is not really y, it's negative 2t. And n is 5. Well, if n is 5, everyone, if n is 5, we're looking at the 6th row. So it's the same set of numbers. It's still 1, 10, pardon me, I got a little distracted there. It's still 1, 5, 10, 10, 5, 1. So it's still 1, 5, 10, 10, 5, 1. So I'm going to have 1 times my x, which is 3r raised to the 5. Look at where that exponent of 5 is. It's not just on the r, it's on the 3r. And then plus my next coefficient is 5. And I'm going to have that x, which is 3r raised to 1 less. And then I will have negative 2t raised to 1. That's my y. So this is my x to the 5. This is my x to the 4, y to the 1. That's what's happening. Continuing on, I'm going to get 10. My 3r now, which is now to the 3, is multiplied by the negative 2t, which is to the 2. Continuing on, I'm going to have 10, and then my 3r to the 2, my negative 2t to the 1. Pardon me, my negative 2t is to the 3. My negative 2t is going up by 1 each time. Then I'm going to have plus my 5. 3r will be to the 1. My negative 2t will be to the 4. And then I'm going to have finally 1. My 3r will be to the 0. I'm not even going to write that. We don't have any 3r's anymore. What I do have is negative 2t to the 5. But now things get a little more complicated, because the coefficient of my first term is not going to be 1. It's going to be 243, because 3r raised to the 5 is 3 to the 5 times r to the 5. And 3 to the 5 gives 243, which you can check on your calculator and which I am going to check on mine as well. I'm pretty sure that's right. But I want to get a calculator in front of me just to double check. $243. My second term is not going to have a coefficient of 5. It's going to have a coefficient that contains a factor of 5. It's also going to contain a factor of 3 to the 4. And it's also going to contain a factor of negative 2t to the 1. All of these things I'm about to highlight, everybody, contribute to the coefficient. And we'll worry about what that number is in a second. But we're also going to have an r to the 4 and a t to the 1. My next term, well, there's going to be a 10. There's going to be a 3 cubed. There will be a negative 2 squared. And then we will have an r cubed t squared. Again, all of the things that I'm highlighting are contributing to the coefficient. 10, 3 cubed, negative 2 squared. Then I'm going to get 10. I'm going to have 3 squared and negative 2 cubed, and an r squared and a t cubed. Once again, the coefficient is an amalgam of many different pieces. We also have, moving on to the next term, 5, we will have a 3 to the 1, a negative 2 to the 4, and then we have an r and a t to the 4. Once again, the coefficient of that term is going to be what it is because of the 5, the 3 to the 1, and the negative 2 to the 4. And finally, we have negative 2 to the 5, and then t to the 5. And now we have to clean this all up. And I just want to double check everything. (3r) is to the 5. I'm looking at the top of the screen. Then it's to the 4. Then it's to the 3. Then it's to the 2. Then it's to the 1. Then it's to the 0. My negative 2t in the first term is not there, which is good. Then it's to the 1, then to the 2, then to the 3, then to the 4, then to the 5. I've got my numbers from Pascal's triangle, and now I put this all together. So you're going to need your calculator for this part. We have 243 r to the 5, plus I need to calculate on my calculator what 5 times 3 to the 4 times negative 2 to the 1 is. And I get negative 810, so we can write minus 810, and it is an r to the 4 t to the 1. Now what I'm going to do is go over here and calculate what this whole thing is. 10 times 3 cubed, which is 27, times, look at how I enter negative 2 squared. I put that negative 2 in brackets. That's important. 1080 plus 1080. This is r cubed t squared. Now I'm moving on to what's underlined in black for a coefficient. 10 multiplied by 3 squared, which is 9, multiplied by, in brackets, negative 2 quantity cubed. Gives me negative 720. So minus 720, and that is r squared t cubed. Now I'm going to look at what's underlined in squiggly brown. 5 times 3 to the 1 times negative 2 in brackets to the 4. 3 to the 1 is just 3. I get 240. So my final term, not my final term, that term is 240. rt to the 4. Finally, negative 2 to the 5 is negative 32. T to the 5. It's a bit of a journey for that one. There's a lot going on there. You can certainly double check all of your coefficients, not coefficients, your exponents. It's r to the 5, then r to the 4, then r cubed, then r squared, then r to the 0. It's t to the 0, then t to the 1, t to the 2, t to the 3, t to the 4, t to the 5. It looks okay. Now what we're going to do is just take a quick peek at an even more economical shortcut, one where we don't have to expand the whole thing. And what I would like everybody to do is focus your attention up here. You can look at the next page if you like. And at the top of the next page is a diagram, but that diagram will not match what we're looking at here. I want you to focus up here, please. There's Pascal's triangle, and on the right-hand side, I've got the coefficients of the expansion of which binomial each row is. So this first row is the coefficient in the expansion of x plus y to the 0. The second row are the coefficients of x plus y to the 1. The third row, the coefficients of x plus y to the 2. But just don't worry about where this is going just yet. I want you to focus on that 1 at the top of the screen. That 1 at the top of the screen could be written as 0, choose 0. It could be. If I said to you, you have 0 items to choose from, how many ways can you choose none of them? The answer is 1. 1 is 0, choose 0. I want you to notice in the second row that that first 1 is 1, choose 0. How many ways can I choose no items out of 1? Well, only one way. And the second number is 1, choose 1. In the third row, that first 1 is 2, choose 0. The 2 that comes after it is 2, choose 1, and then 2, choose 2. And this pattern continues. This 1, 3, 3, 1 is 3, choose nothing, 3, choose 1, 3, choose 2, 3, choose 3. The 1, 4, 6, 4, 1, 4, choose nothing, 4, choose 1, 4, choose 2. And this is the diagram that I'm giving you in your notes. 4, choose 3, 4, choose 4, and it continues. The beautiful thing here, everybody, is the following. N is the number you're choosing from in each row. So if n is 1, it starts off with 1, choose nothing, and then it goes up to 1, choose 1. If n is 2, it goes from 2, choose nothing to 2, choose 1 to 2, choose 2. If n is 3, 3, choose nothing, 3, choose 1, 3, choose 3, 3, choose 4. Sorry, let me repeat that. 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. Why is this a nice thing? Because I don't have to look at Pascal's triangle anymore. If I want to expand x plus y to the 7, I'm going to use for coefficients 7, choose 0, 7, choose 1, 7, choose 2, all the way up to 7, choose 7. And I'm going to get 8 numbers. You can count these on your fingers. 7, choose 0, choose 1, choose 2, choose 3, choose 4, choose 5, choose 6, choose 7. I've just counted off 8 numbers on my hands. So we're going to use this idea with one final example. And I'm going to make an attempt to make things even simpler for you, where we don't have to start looking at the first term to get the second term to get the third term. But that's what we're going to do to begin with. Since n here is 9, our first term will have this for a coefficient. 9, choose 0. It will contain a 2x to the 9, and it will contain a negative 3y to the 0. We're after the fifth term, but just don't worry about that just yet. My next term will contain 9, choose 1. We start off with n, choose 0, and we go up by 1 each time. It will contain 2x raised to the 8, and it will contain negative 3y raised to the 1. I want to point something out to you. This is really at the heart of things. This number will always match this number. It's 9, choose 0, and we have negative 3y to the 0. It's 9, choose 1, and we have negative 3y to the 1. Our next term is 9, choose 2. It's going to contain 2x to the 7, and it's going to contain negative 3y to the 2. the number we're choosing out of 9 matches the exponent on that part of the term. And finally, and then we can answer this question and you can get some practice. This number here is what I'm going to be referring to as a key number. The key number for this term is 0. The key number for this term is 1. The key number for this term is 2. But this is the first term. This is term 1. This is term 2. This is term 3. And what I'm getting at is the key number, which is the number that matches the exponent on y, and the number you're choosing from n. That key number is always 1 less than the term number. So if you wanted to find the 5th term, the key number is 4. The key number is 1 less than the term number. Which means the 5th term will be 9. Choose the key number. It will contain 2x raised to an exponent. It will contain negative 3y raised to the key number. And the exponent on the 2x has to be something that adds to the key number to give 9. Because those exponents have to add to give 9. And I'm going to end this lesson here. Actually, I shouldn't. Let's finish this off. We need to figure out what the 5th term is. The coefficient will be 9, choose 4. It will also contain a 2 to the 5. It will also contain a negative 3 to the 4. And it's going to have an x to the 5. It's going to have an x to the 5, y to the 4. So we really ought to figure out what 9 choose 4 times 2 to the 5 times negative 3 to the 4 is. Nine choose 5. Nope, 9 choose 4. Multiplied by 2 raised to the 5. Multiplied by, in brackets, negative 3 raised to the 4. Gives me a whopping 326,592. X to the 5, y to the 4. And that's the 5th term. But you should be able to now, using this idea of a key number, which we will formalize tomorrow, you should be able to determine any term without determining all the terms before it. Anyway, it's a difficult lesson for me to go through just on video because I can't see your expressions. I can't tell how well you're getting this or not getting this. I have a hard time with how fast I'm going or how slow I'm going, so I hope that went well. We're going to continue working on this tomorrow. Some basic questions with the binomial theorem on page 542 of your text. And if you do get that done in class, then you can certainly work on some extra practice problems outlined up here that can be found in your unit handout. In the meantime, I'll be very happy to be back in class with you tomorrow, and have a great rest of the day. We'll talk to you soon.